Okay, well, thank you very much for having me speak here. Yeah, so feel free to interrupt me as well at any point of the talk if I go too quickly or if something is unclear. And also 2 of my co-authors should be present in the audience in the chat maybe to answer some questions as well. Yeah, so what I'll be talking about are cyclically covering subspaces, and I'll introduce them later. But yeah, one of the things that I found really fun about this project was that it actually connects up with lots of different notions, and there's also still quite a lot of nice open questions. So even if you don't end up liking the cyclically covering subspaces, maybe there are some other things that you will be interested in this talk. And yeah, everything here was joint work with James Aaronson and Tom Johnston, who are also PhD students at the University of Oxford. And yeah, it was really a fun project to work on because of this as well, because we spent quite a few months thinking about these problems together, which was very enjoyable. So yeah, to introduce the cyclically covering subspaces, I'll first talk about something slightly different, which was the original motivation of starting to study these. And I'll start off from the following question. So suppose that we have 2 types of coffee machines, and we need a new one for our department, and we have a group of n mathematicians. So everyone will vote for their favorite one, and now we need to decide which one we take. So if n is odd, we all know how to do this. We just do the majority rule. But for n even, it's not that clear how we're going to do this decision procedure. So let's maybe treat this a bit more as a mathematical problem. Suppose that we look at the subsets of the integers 1 up to n. And now for each subset, we can record whether the first alternative will win or not. So suppose that our winning coalitions, whenever such a subset votes for 1, 1 will actually win. So what are some natural properties here? Well, if more people vote for an alternative, it's more likely to win. Alternatives are treated fairly and voters are treated fairly. These are all 3 sort of natural things we may want for some kind of voting rule. So let's put in some mathematical terms for this. So this first condition is kind of easy what you should do. Whenever you have a winning coalition and there's something bigger, then it also needs to be a winning coalition. And the second one is also kind of easy. Well, alternatives are treated fairly, then quite a natural assumption is that both the set of winning coalitions and the set of losing coalitions is equally big. So this first one is also called an upset, and these 2 things together, they actually give a thing in combinatorics called a maximal intersecting family. So this is actually something that some of you might know about. And now this third one, it's maybe a bit more, more specific, but an assumption that you could put on is that the automorphism group of the set system is transitive. So an automorphism just means that we map the voters to the voters, and we want to send each winning set to a winning set. And then transitive is just the usual sort of group property of transitive. So you don't have to remember these things or know what these are, but there are some kind of conditions on this, and someone started studying these and called these homogeneous games. And for n odd, we can actually find such a homogeneous game. Namely, we can take all sets of size strictly greater than half of the set, and that's also known as the majority rule. So we know that these exist. So now the question is basically, when do these exist for n even? And there's actually various views of this. So the first thing you can do is you can call these homogeneous games. But they're also known in combinatorics as symmetric maximal intersecting families. And for the people who really are more into group kind of things, you can actually also ask instead for transitive subgroups of the symmetric groups on n numbers, such that each permutation of order power of 2, so each permutation which has as an order something of the form 2 to the I for some I, must have a fixed point. So something in about these sort of permutations. And it's actually not known for which n this exists. And there's a conjecture about this from the 1960s called Isbell's conjecture, which is still open, and basically not much about it is known as at all, which is that for each odd integer b, there's only finitely many n of the form n is 2 to the m times b. So remember that we could do odd numbers, but then when we have an even number, if there's sort of too many factors of 2, then he conjectured that it would no longer be possible to construct these things. Okay, so how does this relate to our cyclically covering subspaces? Well, small cyclically covering subspaces give large fair games, large homogeneous games. So Peter Cameron was interested in Isbell's conjecture, and he noticed that this notion that he introduced, this cyclically covering subspace, if we have done one of codimension M, then we can use one to construct such a homogeneous game. So the construction is not super difficult, but it's also not really super easy that I would have time to show it now. But this was the original motivation for these. But I just wanted to mention this conjecture as well, because I think it's a very nice conjecture. Okay, so what I'll be talking about in this talk are these cyclically covering subspaces. And the first thing to define is the cyclic shift. So I've just given an example here for n is 3. So what the cyclic shift does is that it just sort of shifts around the entries of a vector, and then we turn it all the way around. I see that there's a question in the chat. Is spelled if and only if cyclically covering. So Isbell's conjecture, like there's not really a conjecture yet about the cyclically covering subspaces, but so you probably mean whether you can get a cyclically covering subspace from a fair game. And yeah, the construction only goes one way that he gave. Maybe it is, maybe you can use it somehow, but I actually think that maybe that's already known to not be possible. But yeah, it's the cyclically covering subspace can be used to define a fair game. Or in fact, what he defines is this sort of transitive subgroup, which then can be used to give a fair game.
Is there any conjecture about exactly which n will give you this thing?
So yeah, they define this value m of b, so sort of the smallest m, for which this is like the point up to which this is possible. And there's only, I think it's only known for the values b is 1 and b is 3, what this value is. And yeah, even after that, they know very little about it. So yeah, they don't know it. Yeah, they basically don't know anything about this yet. This is sort of my, I mean, they have some results, but there's a lot to be found still, I guess. A lot of open questions. Okay, so for the cyclically covering subspaces, what do they mean? Well, they're linear subspaces of f2 to the n, and f2 is the finite field on 2 elements. And the condition is that every vector has some kind of shift which lies in the subspace, or equivalently, we could take our subspace and we could shift around all the elements in the subspace and then shift all the elements again, etc. And then take the union of that. So each time we shift something n times, we get back to where we were. But the condition is that eventually all of these shifts, they need to cover our entire space. And something that I put here at the top that I forgot to mention now is that through this talk, it will be convenient to see these indices mod n. So I'll sort of number them 0 up to n-1 typically. Yeah, so this is the definition of a cyclically covering subspace. So now maybe to see if people have understood it, can someone give me an example of a cyclically covering subspace? So there's one easy example that exists for every n.
The whole space.
Exactly, yeah. So sort of an easy example of this is just to take the whole space. So we always have some cyclically covering subspace. And we also can never make it too small because we always need the all ones vector to be in it. Because whenever we start shifting this around, it just remains the same thing. So we just need to put it in. And to sort of give a sort of non-trivial example, for n is 3, we can take this space. So we see that we've covered the vector 0, we've covered all the sectors with 1, 1, all the vectors with 2 1s, and we've also covered the vector with 3 1s. So everything is covered here. And this has dimension 2. Okay, So what we'll be interested in actually is sort of how small can we make this? So remember that this was also what we were interested in for the homogeneous games, because small cyclically covering subspaces gave sort of large fair games. And therefore we define this quantity h2 of n, which is just the largest codimension that we can get. So note that the codimension is just n minus the dimension. So we just take the best sort of possible cyclically covering subspace, and then we look at the largest that we can make this codimension. Okay, so just to check again that people have understood this definition, can someone tell me what h2 of 3 is? Someone has already posted 1 in the chat. So this is indeed 1. We saw on the previous slides that we had this example here of codimension 1. So that meant that it's at least 1. And now it's also quite easy to see that we need to put in the all zeros factor, the all ones factor, and then we haven't covered everything yet. So it's also at most 1. Okay, so there's also another upper bound that we can get quite easily. So I'll just explain that as well to give you a bit more feeling about these cyclically covering subspaces. So whenever we have a cyclically covering subspace, by definition, this thing is the whole space. And the whole space has 2 to the n elements. So that gives this equality. And now sort of worst case, each of these shifts is unique. Each of them gives sort of all new elements. And we have n of these shifts. So worst case, this is n times the size of phi elements. But we know that phi, it's a linear subspace in f2 to the n, so we actually know the number of elements. And now we can just bring this n upstairs as well. And we can take the 2 log of this equation, and then we find this, that n is at most the dimension of phi plus the log of n. And we can just rearrange this to get a bound on the codimension. So we just bring the dimension to the other side, and we see that the codimension is at most log n. So what we showed now is that if phi is cyclically covering, then the codimension is always at most log n. So that gives us an upper bound. And this was shown by Cameron, Alice, and Raynaud. So you can always take the floor as well, of course, because it's an integer. But they also showed that this can always be attained. So they showed that whenever n is of the form 2 to the d minus 1, then this inequality is actually tight. And we saw before that h2 of n is always at least 0. We saw that we can always take the whole space, and that's actually attained as well. So it's actually 0 exactly when n is of the form 2 to the d. So it's 0 when n is of the form 2 to the d, and also otherwise it's greater. And that follows from the 2 results below that. So it's at least 2 whenever n is at least 5 and odd. And from the inequality below that, we see that whenever we add sort of 2's here, the value cannot decrease. So as soon as for one of the prime factors it's positive, it will remain positive. Yeah, so this gives us some information already about what these numbers look like. So when we started studying this question, actually, one of the first, oh, sorry, there's another question. Can you say something about the example achieving tightness for n is 2 to the d minus 1? Yeah, so they look at quite sort of different techniques than we do. So they very much take a representation theory-like approach to the cyclically covering subspaces. And yeah, they somehow semi-explicitly construct things for these cases. But yeah, I wouldn't be able to immediately say something super interesting about their example. But they use quite different techniques than we do in our paper. And in fact, what we do is that we first reformulate the problem to look at the orthogonal complement. So here we were looking at maximizing the codimension, but when we move to the orthogonal complement, we can actually talk about maximizing the dimension of the orthogonal complement instead. So to some extent, that's a bit more natural. So just some definitions. We find the dot product just by taking the element-wise multiplication and summing up. And then the orthogonal complement is just a set of vectors which have dot product 0 with every factor in the set. So this is just sort of the usual orthogonal complement. And whenever we have, because we have like a finite dimensional space, whenever we have some kind of subspace, we can always just take the orthogonal complement and we can write it in the form, we can just take a basis for this orthogonal complement. So we can write any cyclically covering subspace as some kind of orthogonal complement of m factors. And now instead of having maximal codimension, we just want to find m as large as possible. So we want to find factors v1 up to vm with the special property. And this property, so originally we wanted to say that each vector has some kind of shift in the subspace. And now this translates to asking for every vector to have a shift which lies in this orthogonal complement, so which dot products to 0 for all the vectors. And now this fact that that all ones vectors in the subspace, if you just look at this condition here, there needs to be some shift of the all ones vector, which dots to 0. But all of these shifts are the all ones vector. So we get that the all ones vector dot our vector needs to be 0. So this is all sort of taking mod 2. So in fact, that sort of tells us that we want these, we want all of these sum of the entries to be even. And that needs to be the case for all of these VI. So that's what I call the weight. This is the sum of the entries. I don't know why I managed to lose my chat now, but maybe other people can answer. Okay.
There's a now kind of gray box over a bit of the slides.
There's a what?
Oh, now it's gone.
Okay. Okay, so this is the formulation that we looked at. And one of the first things was that we tried to reprove some of their results in our new formulation. And eventually that resulted in this result of ours. So remember that they lower bounded it by the max of h2m and h2n. And we had several weaker versions of this result first, and eventually we sort of found this quite pleasing result that we can actually lower about h2 of m times n by h2 of m plus h2 of n. And I won't say too much about this proof, but just to give the basic idea, from h2 of m, that just means that if h2 of m is, say, equal to 10, that means that we can find 10 linearly independent vectors with this nice shifting property. So we can take these 10 vectors and then we can lift them to our bigger space, and we can do the same for h2 of n. So this way we get h2 of m plus h2 of n vectors in our bigger space. And then the only thing to do is to show explicitly that these work as well. And the thing in this case, what we do is we have some kind of explicit construction that plays nicely with the shifts. So this is after that, it's just sort of a bit of calculations. But what I wanted to talk about in this talk is our sort of main result of the paper. And that's relating to a question of Peter Cameron, who asked what the behavior was of h2 of n over the odd integers n. So he asked whether it tends to infinity or whether it remains bounded by 2 for infinitely many odd n. So I don't know why he asked the upper bound 2. There's a lower bound of 2 that might have been known by then already. But initially there would have sort of been 3 possibilities. We could have had that it converged to infinity. It could be that it's bounded infinitely often. And in that case, either there could have been some bad prime for which there are a lot of, for which these prime powers are all bounded, or there could have been infinitely many primes for which it's bounded. And by our previous result, the first case is already no longer possible, because one of the corollaries is that whenever we take a prime power, this will always tend to infinity. And basically our main result states that the second case is true, assuming you're willing to assume some number theoretical conjectures. So for example, the generalized Riemann hypothesis would suffice. So what we show is that h2 of p is equal to 2 for all primes in a set of primes which is conjectured to be infinite, but it's not known to be infinite. So we can show it for all primes for which this polynomial 1 plus x up to x to the p minus 1 is irreducible over f2. And then we also say that such a prime, equivalently, such prime p has primitive root 2. And it's widely believed that, I mean, I guess the audience will know more about this than me, but yeah, we were told that it's widely believed that there are infinitely many such primes, and it's actually a special case of Artin's conjecture. And he, in fact, didn't just conjecture that there are infinitely many such primes, but he conjectured a precise density, and not just for the value 2 actually, but also for other values. And there's quite a few results known about, about some special cases. Like, for example, I think there's only one prime which will fill out of the primes 2, 3, and 5 or something like this. Some results like this are known, and overall there are only 2 primes that fill. So hopefully it's true. But for now, there are quite a few primes for which we still prove it for. For example, all these primes here on the bottom, our result will hold for all of these primes. And just to give a one picture proof of Artin's conjecture, what I've plotted here are the primes for which the density of the Artin primes among the primes for the first few numbers. So we see here is the conjecture density from Artin, and yeah, it seems to be going pretty well. So there's another, we should assume p strictly greater than 3 in the previous statements, right? Oh yeah, that's true. Yeah, maybe I should have kept it at most. Okay, so yeah, so this is the main result. And I'll first tell you a little bit about why we need this polynomial to be irreducible. And then for the rest of the talk, we can actually forget about it because we only need it for sort of a first case. So when we have a factor in f2 to the p, we can actually associate a polynomial to it by taking the entries of this factor as the coefficient for the polynomial. And if we now look modulo the polynomial x to the p minus 1, then multiplication by x is actually the same thing as shifting, because as soon as we sort of, the v0 will become v0x, so that will shift 1 to the right, etc. And then vp minus 1 will loop all the way back. And this was actually something that Cameron, Ayles, and Raynaud used as well for their constructions. The reason that we use this is that if we now take this polynomial ring, we can factor it into 2 parts. The first of which is always a field, and the second of which is a field if and only if this polynomial that we were interested in is irreducible. So that's where it comes in. If this polynomial is irreducible, then this is a field and we can start inverting elements. So the claim that we use it for is that if we know that h2 of p is at least 3, so it isn't smaller than 2, then we can assume that we have found some kind of cyclically covering subspace, and now we want to assume that one of them takes a certain form. So we want to assume that one of them is of the form 0 and then all ones. And what we do now to get this is that we take the polynomial corresponding to u, and we find some kind of polynomial which multiplies it to the polynomial of the 0 or 1s vector. And then p prime and w prime will also be defined like that by just taking the polynomial q and multiplying f of v and f of w. And then what we need to show is that this sort of preserves the required properties. But yeah, the point where it really comes in is being able to define this polynomial of q, which we want to be 1 mod x minus 1 and fu inverse mod this other polynomial. And that's the only point where we use it. So for the rest of this talk, I'm going to assume that one of the factors is of the form 0 or 1, and we're going to forget about polynomials, and we're just going to consider an arbitrary prime p. Because for arbitrary prime p's, we can show that such a subspace doesn't exist. Okay, are there any other questions about this so far? The results are... Okay, so we proved this result by a case analysis on the structure of the vectors v and w, and therefore we the notion of a symmetric vector. So we call a vector symmetric if the 0 entry is 0, and if the I entry is equal to the minus I entry for all I. So just to give an example, so I will start counting my vectors. The first entry, this will be 0, this will be 1, 2, etc. So if v0 is 0, there's a 0 in the first entry that's satisfied. And this 1 entry is equal to the minus 1 entry here, and the 2 entry is equal to the minus 2 entry. And for this one, it goes wrong because there's the 1 entry and the minus 1 entry are different. One of them is 1 and the other is 0. And on the last one, it doesn't work because of the first entry not being a 0. But the rest of it was satisfied. So that's a symmetric vector. And what we can show is that if either v is symmetric or w is symmetric, then no such cyclically covering subspace can exist. And then the main part of our proof is to show that they can't both be sort of not symmetric. And actually, when we were attacking this conjecture, we actually thought that this lemma was going to be the hard part. So in the end, it turned out to be quite a bit less work than the rest of our paper. But we actually conjectured the following result based on computer experiments, that actually even if we take something smaller, so if we remove one of the factors from the orthogonal complement, then of course the subspace itself becomes bigger. So it's easier for the 0 or 1's vector and v to together have an orthogonal complement that is cyclically covering than if we add something else. And we already thought that just adding one such non-symmetric vector would not be possible. So we conjectured that this subspace is cyclically covering if and only if the vector v is symmetric. And there's a weird condition here that we add, namely that 7 doesn't divide n. And that's because for n is 7, it's actually false. And then also you can lift this example to all multiples of 7. So the counterexample looks like this, and then you can do some sort of standard transformations to these to get all the counterexamples that that we were able to find. At least this is the case up to n is 43. So right now this conjecture seems a bit arbitrary and possibly uninteresting because you might not have heard about cyclically covering subspaces before this talk. It's a bit of a random vector, the 0 or 1's vector. But later in the talk, I'll give a second formulation of this conjecture, which might seem a bit more appealing to you and maybe also a bit more true. Okay, so actually for the rest of the talk, I'm going to again reformulate the setup, and we'll be looking at that. So our goal will be now to prove this conjecture, which we won't manage to do. But then I claim that the sort of the insights we have still help for proving the theorem. So now we're going to look at when can such subspaces be cyclically covering, so with the 0 or 1's vector and v. So for this vector v that we have, we're going to associate a graph, a Cayley graph. And the generating set will be the support of this vector v. So what we do is that we have a vertex set modulo n set, and we draw an edge from k to k plus I whenever v of I is equal to 1. So just an example here v of 0 is 0, so there's no self loops. And v of 1 is 1, so there's an arc from 0 to 1 and from 1 to 2, etc. But there's no arc from 0 to 2 because v2 is 0. And similarly, there's no arc from 0 to 3 or 4, etc. And here we see that -1 is not allowed, -2 is not allowed, but -3 is allowed. So again, we see arcs from 3 to 0 and from 4 to 1. So this is the Cayley graph, which we can draw for each vector v. And now we also want to associate something in this Cayley graph for our test vectors x. So whenever we want to see for vector x how it's sort of in this cyclically covering subspace, like how there's a shift in the subspace, we look at a certain induced subgraph. So if we have the vector of this form here, then there's a 1 at position 0, so we put 0 in the subspace. And there's a 1 at position 1, so we put 1 in the subspace. But for example, the element 3 is not in the subspace because there's a 0. So we just look at the support of the vector x and then look at the graph induced on that. And that will be our induced subgraph. And it turns out that the size of this subgraph and the outdegrees in the subgraph tell us something about whether or not x can be covered by the union of the shifts of the sort of the space that we consider. So we can associate this sort of product that we're interested in with the outdegree of the element k to this subgraph somehow. So I won't go into detail of how this works, but what we do get is that the following two statements are equivalent. So the fact that this subspace is cyclically covering, what we were interested in, and this Cayley graph that we define for the vector v having no odd-sized induced subgraph with all outdegrees odd. And all outdegrees odd, we could also replace that with all indegrees odd.
So we have a question in the chat.
Okay, yeah.
I think it's about previous slide.
It's possible v minus I is 1 per some I, and the digraph is not simple, right? Yeah, so in this case, I haven't drawn any double arcs, but in principle, we could have double arcs. We could have an arc from 4 to 1 and from 1 to 4. Thanks for asking. Yeah, so we can show this equivalence. And so instead of trying to prove that that it's not cyclically covering for non-symmetric v, we can also try to find an odd-sized induced subgraph with all outdegrees odd. And now our conjecture can be rephrased as follows. So this first property that we had was that this thing is cyclically covering. So in this case, this becomes that the Cayley graph doesn't have an odd-sized induced subgraph with all outdegrees odd. And the second property that we had was that v is symmetric. So for v symmetric, the first property was that v0 is 0, and that exactly gives you sort of no self-loops. And the second property was vi is equal to v minus I, and that exactly tells us that there's no single direction arcs. So either the arcs, there's an arc from one side and from the other, or there's no arcs at all. And that's also known as just a graph, like there's just a simple undirected graph. Okay, so now let's step back and look at this conjecture again. And actually one of the sides of this conjecture has become quite trivial. So if you remember the handshake lemma, it says that whenever we have a simple graph, we always have an even number of vertices of odd degree. So if we assume that we just have a graph, then we don't have any odd-sized induced subgraph with all outdegrees odd, just because, well, such an induced subgraph is again a graph, and if all the degrees were odd, then we know it needs to have even size. So this part already showed us that whenever v was symmetric, we actually knew that this thing was indeed a cyclically covering subspace. But for v non-symmetric, what we can now try to show is that we can actually find such a subgraph. So let me just sort of recap the situation that we're in. We're looking at some kind of prime. we've got some kind of non-symmetric vector. And if V0 is 0, we're already done, because just the self loop itself is an odd-sized induced subgraph with all out degrees odd. So we can assume that it has some kind of single direction arc. And then we can redefine this sort of graph corresponding to the vector V. And now we want to find a bad subgraph in that. So some kind of induced subgraph on an odd number of vertices, either all vertices have odd out degree or all vertices have odd in degree. And one of the first reductions that we do is that actually we assume that there's no two loops. So there's no double edges. So what we can show is that you can always, if there are two loops and there are sort of non-edges, and we have this sort of non-symmetric vector, that then we can find a bad subgraph. So after that, up to taking complements, we can assume that there's no double edges. So that we'll have that assumption in the rest of the talk. So there's no self loops, no double edges. We just have some sort of plain directed graph. Okay, so we didn't have any self loops or two loops. So what is the smallest sort of cycle that we have? Well, as soon as that's odd, we're also done. Because if we look at an induced cycle, it's an induced subgraph with all out degrees equal to 1. So all out degrees are odd. And if it's of odd size, then we're ready. So we can assume that when we look at the smallest cycle in the graph, not necessarily induced. If we look at the smallest cycle in the graph, then it is necessarily induced. So if the length of the smallest cycle is odd, then we're immediately done. So we know now that it needs to be 4, 6, 8, etc. And what we actually can show is that for whenever it's at least 8, we have some kind of argument to get rid of it. And when it's 4 or 6, we can't prove our conjecture, but somehow we can still prove our theorem. So this is really when we start using this is really where we start using some big additive combinatorics results. So what we do is that we show that for some kind of sum set, so I'll define this later on, some kind of sum set doesn't contain the element 0 based on the fact that there's no smaller cycles than length k. So due to the fact that there's no small cycles, we get some kind of additive property. And from this additive property, we then find that this set is contained in a small arithmetic progression. And this set S is defined as the set of indices for which Vi is 1. So that those were exactly the edges in our graph. Those were exactly sort of the lengths of the edges, let's say, that our graphs could have. And from the fact that it's in a small arithmetic progression, we get some kind of structure on the edges. And then we can explode this structure to find a bad subgraph. So that's the game plan of our proof. So let me just first define this first thing and show you how that works, because that's actually quite easy. So we just define A plus B as usual as the set of A plus B for A and B and B. And then when we write 2A, for example, that's just the set A plus A. And more generally, we can define KA like this. And some results that we actually used in some of our lemmas as well before are the Cauchy-Davenport inequality and phosphorus theorem. So I won't really need them in the rest of the talk, but I thought I'd maybe mention that we use these. So phosphorus theorem just tells us something about equality case in Cauchy-Davenport. So Cauchy-Davenport tells us something about how big such a sum set can be. And then phosphorus theorem tells us that if we achieve the minimum, then actually these sets need to be arithmetic progression. And we'll need some kind of theorem like this where we say that, oh, if we have things for which the sum sets are really good, then they're contained in a small arithmetic progression. So I'll show that later. Okay, so if we let k be the length of the smallest cycle and s be the support of v, then if we know that 0 is in 4s, what that means is that we can find 4 elements in S which sum to 0. So let's call them A, B, C, and D. And now this actually tells us that the graph induced on this subset needs to contain a 4 cycle. Namely, if we look at 0 to A, well, the difference is A, and that's in S, so there's an edge there. And from A to A plus B, the difference is B, so again, there is some kind of edge there. And the same for this last one. And now finally, if we go from A plus C to 0, then we know from this equation that that length is equal to D. And again, there is an arc from A plus C to D to 0. So we know it contains some directed 4 cycle, not necessarily induced, but the length of the smallest cycle is at most 4. So this tells us in particular that 0 cannot be contained in k minus 1 times S. And also not in k minus 2 times S, k minus 3 times S, etc. And you need to think a little bit about this, but like a sort of short way to write this is in this form. So we can't, here we can sort of take 0 whenever we want to take less elements as well, if we don't want to take k minus 1 elements from S. So note that 0 is not in S itself yet because V0 was equal to 0. Okay, so now we have just shown that this thing misses 1 element, but actually this already gives us some bounds on the size of S from Cauchy-Davenport, and also we can use it somehow to apply this sort of more scary looking result, which is a corollary of a result from Grinkovich. So it's some kind of analog of Feynman's 3k minus 4 theorem, which works in the integers. And there it says that if we take the sum set and it's at most 3 times the size of the set minus 4, then we're contained in some kind of small arithmetic progression. And this result has the same conclusion. And the first assumption is very similar, but slightly weaker. Like this 2 is smaller than this 3. And we also need a second assumption. So it's actually necessary to put some kind of assumption here about it not taking up too much of set modulo p set as well. Yeah, so this is the result that we end up applying. And then finally, what we get is that this set S is contained in some kind of small arithmetic progression. And we can also prove these bounds on S. So S is actually quite dense in this arithmetic progression as well. Slightly stronger, Grinkovich says stronger. Yeah, that's what, yeah, indeed. Yeah, this is actually slightly stronger. I meant that this is indeed a slightly stronger assumption. So the result is weaker, let's say. Yeah, so what we find is that this set S is sort of dense in some kind of small arithmetic progression. And because we're working on set modulo p set, we can actually assume that this common difference of the arithmetic progression is 1. So sort of the picture you can have in your mind is that there's a sort of interval of lengths that are allowed for our edges. And it's all concentrated in a small interval. And this information we then use to either construct an odd cycle or an even cycle with one thing pointing to it. So there's a bit of case analysis that goes into that. And then finally, all this works for us whenever k is at least 8. And so we can prove our conjecture in that case. And then for case 4 and 6, we still need to do other things. And there's a bit more case analysis involved. And we don't manage to prove our conjecture. Okay, so yeah, in the end, I'll now mention some open questions. So we first have quite a few open questions still directly related to our work. So one of the other results that we can show is that h2 of 2n is at most twice h2 of n. So we had some kind of lower bound for these factors, but then for m is equal to 2, we can also get some kind of upper bound. But when we have m equal to 3, we don't know if that's the case already. So yeah, we think it's quite one of the questions that we pose is whether we can find a similar such result when m is equal to 3. So for whenever we multiply n by 3, that the thing that it increases by is somewhat bounded by the value of h2 of n. And another thing that we think might be interesting to study is when h2 of 2n is strictly greater than h2 of n. So to give an explicit example of something we don't know yet is whether h2 of 3 times 2 to the I tends to infinity. So as soon as we have another prime factor than 2 that appears more and more often, we know that it tends to infinity, but when it's powers of 2, we don't really know what happens. So this is maybe a question which more in the spirit of these homogeneous games. And yeah, another question that we're interested in is to what extent this polynomial being irreducible is a gimmick of our proof. So suppose that instead of the polynomial being irreducible, we assume that it has a small number of factors, say it has only 2 factors. Can you then still bound the value of h2 of p? And the final question, which I think is maybe the most interesting one from this slide, is when HQ of n is 0. So I haven't defined HQ of n yet, but you can maybe guess what it is. So we've now been working over the field F2, but we could have done everything over FQ as well. And in that case, we can again define a cyclically covering subspace in the same manner and HQ of n in the same manner. And for H2 of n, we knew that it was exactly the powers of 2 for which this was 0. But for general Q, this is still wide open. So some results are known, but there's no general classification known yet of when you can do sort of better than just taking the whole space. And actually, yeah, I actually added one more bonus question slide, which is also related to a covering problem, but of quite a different flavor. So if you look at the hypercube instead of f2 to the n, so now we're working in real space, then actually you can always cover it with 2 hyperplanes. So we can take the plane xi is 1, and we can take the plane xi is 0. And those 2 planes will cover the hypercube. But now if we remove the point 0 and we say, oh, we need to cover everything except 0, but you're absolutely not allowed to cover 0, then suddenly we need n planes. So this was shown by Alan Farady using the combinatorial Nussdalen-Satz. So one construction that you can take is just either the layers, or you can take the things of the form xi equals 1 for I in 1 to n, so sort of the sides of the cube. And something that people recently studied is what if you want to cover points multiple times, and they're still that's still very much open. So instead of covering points once, you want to cover them multiple times. But what we studied instead is what if you change this set of points that you're not allowed to cover. So together with James and Tom, and also Andrzej Grzesiak and Bartek Kilak from Krakow, we looked at these questions of, okay, what if we allow larger sets of points where we need to cover everything except that, but we can absolutely not cover S. So if we just fix a number n and then allow S to be anything, then it's something between 2 to the n over n squared and 2 to the n over n. But we don't know which one of the 2 is correct. So that's still open. And also when the size of S is fixed, so we first looked, when we first started thinking about this, we first thought, oh, okay, what if we remove 2 points? It's quite easy to see that in that case, the answer is n-1 planes. And then for 3 and 4, you can still quite easily determine it. So it's n-1, and then the last one, n-1 or n-2, depending on whether you remove the subcube or not. And then for the size of, whenever we fix the size of S and we let n be arbitrarily large, we can show that it's always something between, always n plus some kind of constant depending on S. So it's always between n minus some kind of constant and n plus some kinds of constant. But yeah, we also don't really know what the right dependence on S here needs to be, or whether, for example, you always need at most n planes when n is sufficiently large compared to the size of S. So yeah, there's also some, I think this is also quite a sort of nice question. And actually this first question was also posed by Farady already at Noga Alon's birthday conference. which we found out later. So yeah, I think these are also quite nice questions. So hopefully I've given you some nice questions to think about, and thank you for your attention.